Hello and welcome back to the DOTS lectures. We were in the middle of understanding the discrete up vibration classifier of modules of systems, these symmetric monoidal loose right modules of double categories. And we ended with this idea of how a discrete up vibration of systems theories on the left here gives you such a lax monoidal, lax double, lax right module functor of this form. And so I think that it's worth going through this, but before I do, I'm going to give you some examples of such discrete up vibrations on the right so that we can get a little more deep into what the functoriality on the right, sorry, on the left, on the right hand side entails. So we're going to make a general observation here. Again, another general observation, which is that if for a two monad T, so again, we're th still thinking of this as being sort of the free symmetric monodal loose right module completion monad on, or symmetric monodal loose right module monad on these this diagram of categories. We have a morphism F from A to B, which is colax. So what that means, I think we covered lax morphisms. Colax means that the cell in the middle goes in the opposite direction. So the cell in the middle is going to go up instead of in down. So for example, we can think of this as saying that we go from F A1 tensor A2 to F of A1 tensor F of A2. That's the colax monoidal direction, and this corresponds to saying that F here of some kind of formal thing, which is this, some evaluation of a formal thing, which is this, goes into the evaluation of the functorial application of F. So we're applying it to each component. Okay, so if we have that, then for a strict functor, but well, actually, I don't need to be at this level of generality. Then we may form, this is due to lack, we may form the comma algebra. And it's going to go out. So it's the comma algebra F down arrow B, and it's going to have maps like this, two projections, one to A, one to B, and it's going to have a cell here, and this is going to be taking place in alg colax T. But there's something else going on here, right? Which is that it's also going to be we're going to look at how this would work. So let's look at this from a symmetric monoidal perspective, and which is our good running sort of our up here we did our running example of T being symmetric monoidal category thing. That's great to set intuition because hopefully you have seen a lot of this stuff for symmetric monoidal categories before, and then we can do it in this more general setting of symmetric monoidal loose right modules. So for a symmetric monoidal category, what F down arrow B is, right? It's the actual comma category. So its objects are maps FA to B, and its morphisms are squares of this following form. Well, F of 1 I don't know. So commuting squares of this form. Right? Where this is under F of something, and this is just anything. Pairs of maps like that. And what is the monoidal structure we put on this? Well, it's interesting.
Sorry, so I meant, sorry, did you say T is a two-monad on cat?
T is a two-monad on a two category that has commas.
Okay.
And we can form it, I believe, in that generality.
Two categories has commas, right? But then F down arrow D, where
B, excuse me.
Oh, right, sorry. This is in general, just some object in some algebra.
Yeah, I'm going to describe the category and I'm going to describe its structure. I could, I guess, do it at the abstract level of the T algebras, but I'm going to start with what it would look like in symmetric monoidal case.
Right. Okay. Yeah.
So I'll say e.g. G SMC, and this is e.g. T equals SMC, and then we'll work backwards from that to the case we're interested in. Well, the naive thing to do would just be to take the tensor of both of these things. If this is phi 1 and this is phi 2, this would be phi 1 tensor phi 2. No. Tensor B2, right? But that is not of the form f of something into this. So what do? Well, luckily, we can put f. I'll draw it like this. We can put f like around those two things, and we have this comparator because f was collax. So we define the tensor to be that composite. And there's something important to notice about this, right? And the important thing to notice about this is that the projections have certain special properties here. So when I project out, so what are the projections, by the way, by which I mean these two functors here? They are the things that are taking out this half and this half, right? These maps, underlying maps. So it's pretty clear from this that that the projection on the right projection here, sorry, the left projection is going to be actually strict. Is that right? No, sorry, the right projection is going to be strict. Maybe they are both strict.
I think that's
yeah, they are just both strict. That's right. They test for strictness, right?
I think that this is a lax.
Yeah, look at them. They're both strict.
Algebra has lax limits, and those have strict projections, I think.
Yeah. So yeah, we'll note that this was collax, but these are both strict. Wow. Okay. And right. So cool. So this is the structure we have here. Let's see what that looks like in the case of symmetric monoidal loose right module. Right. So now let consider we have a map F. How about I call it F bar F? Is that what I've been calling these? I don't know. Consider we have a map F bar F from Si to S prime I prime.
So then you have used F bar, but it's that two self-filling the square range.
Yes. Yes. Thank you. So what do I mean by this arrangement of data here? It's a collax thing. How about, yeah, it's a collax thing. Now what we can do is we can form the comma. So what is that? So again, what this means, right, is that we have some S. I'll write it out like this. We have S, we have I naught, we have I1, we have I naught, and some algebra structure on these. Then we have S prime, I prime naught, I 1 prime. Prime not. And then we have f's going like this. And they preserve the structure coaxially via f bar. So what does that mean? Well, we have, let me call all of these f's, right? So we do have this thing where we have s of, say, s1 tensor s2 to f of s1 tensor of s2, right? But we also have things like f of s dot w to f of s dot f of w, and so on and so on. These are all versions of f bar. And they have to satisfy, quote unquote, the evident equations. Oh, and I should say you also have other things. You have the monoidal unit. Um, you have f of the monoidal unit goes to the monoidal unit. And then you have other things like that, including on the W side. Okay. Cool. So given all that, we can form the comma, which I'll still just call f down arrow s prime. And what is this? Well, in fact, because the comma, I should say here, the comma algebra and its underlying object, its carrier, underlying object, is the comma, the comma. And the comma is a certain two categorical limit. So in diagrams of categories, it can be constructed down in cat, in which case it is the actual comma category that I've written out here. So in other words, what we end up with is in fact we end up with f down arrow s prime, or like f down arrow, come on, I prime. This combined, the whole comma algebra, I should say, or is here. It's this diagram with some structure on it. Right? And the structure is exactly the structure of both of these things. So in other words, we would have a system here, right? So a interface here, right, is a map from f of an interface in the top to an interface in the bottom, a type map. And the system is f of a system in the top to a system in the bottom, where they have the appropriate interfaces. And I should say more, not just that they have the appropriate interfaces, but this map has the appropriate interfaces. In other words, this is a system into I, this is a system into I prime, and this is a map over that map.
Sorry, I have a
Yep.
quick question. So for Colax morphisms of these loose right modules,
Yep.
did we talk about these as modules of symmetric nodal categories? This is a diagram in SM
No, I was considering this as
just in
we're adding also the symmetric monodal structure at the same time as the as
oh,
the as the right
right,
modular
okay.
structure. So these are all just categories.
I see.
I think you could factor it out.
Right, okay.
So you could consider them all as symmetric monodal category, as a diagram of symmetric monodal categories.
Okay.
But for now, we're just considering it like this. And then the composition patterns here, again, are square, like a composition pattern here right, is a composition pattern like this, together with a square, um, like this, where this is a square of the form. We have fi1, fw, fi2, I1 prime, 2 prime, to B prime, like that. Okay. I'll make this a lot more concrete in a second because in fact we're always going to take the domain of these things to be a point. So not I guess yeah. In what follows we're always going to do that for at least for a little bit. So maybe I should specialize now and do that. Um, the point so how do we define the compositionality here, right? It's the same sort of idea as above, right? For example, if I wanted to take this and I wanted to form the composite like this, right? What would that be? Well, again, I can form the composite up here, and I can form the composite down here, right? And I want to map them over. This is the same thing, f of I2 to I2 prime. And I want to map them over, but I have to put an f over so I want to take s dot w. I want to put an f on it, but now I need to combine the I need to somehow get from that down to here, right? And what I can do is I can expand it like this using my colaxity. And then this is just the functoriality of dot down below in I prime, or in this module, the bottom module. So this is a lot. I'm going to make this a lot more concrete really soon. The main point is that this thing here, f down arrow s prime I prime, it lives over s prime I prime via a strict morphism. It also lives over s comma I via strict morphism, but we're going to shortly take that domain to be pretty trivial. So we're going to be more interested in this one. And not just is this a strict morphism, and in general, this is not just a strict morphism, but in fact, this here is also always a discrete op vibration in the underlying 2 category. So not necessarily a discrete op vibration of algebras yet, right? But in the underlying 2 category, it always is because it's a comma. And this is sort of an abstract nonsense fact. It's true in cat, and it's true by abstract nonsense. You can prove it in the abstract. I'm not going to do that here. I mean, it's true in cat, and if you've defined discrete op vibrations representably, which we have, then because the limit condition, this is a limit condition, you can just compute it in cat, and it's true because it's true in cat. It's true everywhere because it's true in cat. Okay. So what is the discrete op vibration thing that you have here? Well, if I have some kind of map down here out of an object of the form here, in other words, f a prime to b, and then I have some b to b prime, then there's a very obvious way to push that forward, unique way to push that forward, which is I post-compose by the map down here. So this is an object up here that maps to b. And then I have a b prime up here, so I can lift it to f of a to b prime, the composite, and then this is an obvious map up like there, and then that maps down to here. And it's pretty obvious that this is the unique way you can lift it. So this thing here is a discrete op vibration of modules of systems, symmetric monodal loose-right modules. And this is how we're going to produce them.
Sorry, you said it's a discrete up vibration in the underlying 2 category, but
Yep.
now it's more of a discrete up vibration.
Right. Thank you. If T, I forget what I exactly said, but satisfies the assumptions, these assumptions, then in fact it suffices to check that something's a discrete op vibration in the underlying category. So plus assumptions, which includes familial as a case. Assumptions also a disk opfib of algebras. And so what's fun is that we started with something collax, but then we produced something that is a strict discrete op vibration. So we can take that and move into the lax category and get that it's classified, i.e., there is for any such a thing, we then take this and we go through and we get a map from S prime, I prime to set sliced over span set, which was our omega from last time. And what does it do? What does it do? Well, it sends any B here, any S, let's say. It sends it to the set S in over I, let's say. It sends it to the set S prime, I prime, sorry. It sends it to the set of F of S's, of S's and I's, right? With maps from F of S to S prime and I to F of I to I prime. Right? And all these other things. We're going to go through this in more detail as I specialize this. Okay, so let's take the special case. A very important case, a collax point, i.e., I'm going to call it C, and it's going to go from star, right, if you will, to SI. So what is this going to be? Well, again, I'm going to write S. I'm sorry, this was S prime and I prime before, but now that I only have one of them, S I naught I1 I naught, and then here I put star, 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 star. This is the terminal systems theory or terminal module. And now I'm going to do a map here, C, and then I'm going to call this, call this C. I'll give them all different names instead of just C. It's a little easier. I'll call this IC. I'll call this WC. And I'll call this IC. Okay. So what is this? Well, in other words, we have some system C and some interface IC, and we have some endo composition law IC, WC from IC to IC. We will very often, usually, we will take WC equals the identity of IC. Okay? So we will just often do that. Okay. And there's more data involved because that was just C. Now we also need C bar. So what do we have? Well, we have the collax structure. So for one is for tensor. So we're going to have C to C tensor C. And we're going to have IC to IC tensor IC. And we're going to have WC to WC tensor WC. See. And these all live over each other in the appropriate way. Right? So this thing maps to this one under, right? This maps to this, and this maps to this under all those maps. Right? And we also have another thing, which is we have C. This one, so here's a special thing to observe, is that in fact in here, this is the monodal unit. The single element of the domain here is the monodal unit. I'll maybe put set. Right? So C itself, C is equal to C of this star, which is the monoidal unit. And so it actually comes with a map into the monoidal unit, which is the unit part of the colaxity. And so does everything else. Really, it's id1. And again, this is all preserved by this. And these form a comonoid structure on all of these things, living over all of each other. What does that mean? Well, that's I haven't talked about it, right? But that's the there's some rules to this collax algebra. It's not just a two-cell like this. It has to satisfy some equations relating it to the associativity and unity of alpha and beta. And those rules turn into co-associativity and co-unitivity of these co-monoids. So a monoid, right, would be something like a map like this and a map like this, satisfying some laws. And the categorical dual of that is a comonoid. So I will note, because this is very common for us, if the tensor product is the Cartesian product, then this choice is essentially uniquely determined. It is because it is actually uniquely determined because this is actually not just a comonoid, but a co-commutative comonoid. Because we said it was symmetric monoidal functor. So now it's actually uniquely determined by delta C to C times C and the terminal morphism C to 1. Okay, so it's very often for our system series, if you remember any of our example system series, for them to in fact be Cartesian. So ODEs was Cartesian, for example, as is the behavioral theory. A variety of ones are Cartesian. Even if they're not Cartesian, it's very often that they're co-Cartesian, which doesn't really help us in this direction, but it would help us in the opposite direction. Right? Or we could take their tight dual, where we just flip all the arrows around, right? So in many cases, this part of the structure, it just comes for free. It's not something you have to think about. Okay. Then we also have dot, right? Our colaxity for dot. So what this does, right, is it sends this star dot this star. Sorry. I should be doing this. This star dot this star to C in here and WC in here. So let's write that out, right? We have the image of the composite to the composite of the images, right? The image of the composite here is just C. So again, it's just C. But the composite of the images is C dot WC. And again, this has to be, well, we have another thing. We have more things. We have WC to WC dot WC. Again, why? Because WC is in fact the identity of that very simple double category up there. So it comes with this structure. It in fact comes with its own comonoid structure, but now with respect to composition. So we also have, if you will, id, right? So here, right, we're also going to say that we have WC to id IC. And these two things form a comonoid. Okay. Again, usually WC is the identity, and you won't have to. Usually WC is the identity, and this thing here is also the identity. That's the usual case that we'll consider. But this is what we just get from specializing the definition. And these have to satisfy certain relations, like that I hope are sort of quote unquote obvious or expected, which is like if I do this one and then I do, you know, this, I don't want to give names to this, but like dot to C, dot id, and then now you know that the c dot id ic, and then this is isomorphic to this one, and you want this to commute. Like there's a bunch of things you already have and a bunch of new things you've added, and you can put them together and you want them to commute. And this is going to all be read off from the ultimate abstract nonsense, and it's just a sort of a long road to really do it. And I could go down and do it, but I'd rather us keep moving on and get to a point when we would maybe need to know about that to produce an example. Again, if you take all this stuff on this side, so if you take WC to be the identity and you take this to be the identity, then that comes for free. And if your thing is Cartesian, then this comes for free. And if you make those choices, then you're basically just picking a system with an interface. And that's the most common thing we're going to do. We're going to pick a system with an interface. Right? So, right. Okay. Is this cool? Okay.
And are there sort of other covariance conditions relating? So you've got these two sort of co-modeling structures, one for the dot tensor, one for the cross tensor.
Yes.
And I guess they're like part of the theory is that the dot tensor distributes over what's there must be some sort of distributive law linking these two.
Yeah.
structures.
You're right. That's a good point. Ooh, wow. Okay. So what is that, right? So what we have, right, is that if you take like S1 tensor, so we have this sort of interchange, right? So an S2 dot W1 tensor W2 is isomorphic to S1 dot W1 tensor S2 dot W2. Right. But what we don't have is a is something that what we don't have is anything that tells us what to do with some W that actually has a domain, which is a tensor. And this actually will come up. So what we will find is that the ODE, the more machine style systems, they actually quite like the compositionality theorem I'm going to describe now. But the port plugging and gluing together compositionality of systems, they actually don't quite fit right into this. Which is to say that like again, we started this whole series with the idea that you can represent features and behaviors of systems by maps into them. And what we're now going to do is produce a compositionality theorem by looking at maps into systems from some kind of collax structure on a system, right? That will be useful and important. And it turns out that it's not usually the right one you want for the port plugging one. Say, for example, reachability in Petri nets or something is not this one, but one that uses algebras for double operads. And so we'll come to that later. It's slightly different, and this is one of the nice reasons to do it in this abstract setting. Because if we did this all by hand for symmetric monodal Lewis-Wright modules, and we came to that realization later, it would be kind of annoying. But now all we have to do is check that at least that other thing we're trying to do, algebras for double operads, is also monadic in this special way, which it is essentially because it's familial. It's defined by pictures, and it makes no equations between objects and all these other kinds of things that you need for a nice monad. And so it will have its own representability theorem, which will differ very slightly from this one in that it will have a slightly different it will have a different notion of terminal object and a different and that will give rise to a different kind of collax morphism from the point. Essentially, because it will have multi-morphisms of every arity.
Okay.
And so you end up with a lot more than WC. You end up with a lot of ways to compose C's into other C's. Right? So I won't come to that. But if you had this, you would have something like WCN, and you would have to have something from C into WCN dot C1 C. It's C. C, comma, dot, 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 comma, C. And this actually turns out to be really useful. So, um, for gluing together motifs in models of or like reachability of Petri nets is representable in this form, in the other form, but not in the one we're talking about right now, I believe, for this reason. Okay. Yeah, you get a different compositionality theorem by changing your doctrine too. Maybe the sort of takeaway of this sort of ramble is that it you know, by doing things abstractly, you also give yourself the ability to flexibly change your setting to get the actual result you want through these. Right? You shouldn't just be fixed to a particular way of doing things. But we're going to do this now, and I'm going to specialize. So this is a special case, right? There's the sort of old joke. It's either due to John Bias or Tom Leinster. I can't quite remember who that category theory is the field where your examples need examples, and higher category theory is the field where your examples need examples need examples. I don't know how far we are now, but let's specialize one more time. So now let's do discrete time dynamical systems, more machines. So if you remember somehow back all the way to when we were doing this, these are lenses for the simple fibration, let's just say of sets. This is what I is. And S is going to be of the form SS to IO UE, where these are lenses, right? So, and then the squares are these charts that I've described before. Okay, which will become important. So, okay. So an example here, right, is we might take C equal to B. Well, it's a system, right? So as a system, I'm going to take the natural numbers and the natural numbers, right? And IC is going to, well, it's a system over IC, which is going to be some interface. This is going to be IC, right? And so I'm going to take it to be the natural numbers and nothing. And now I have to give you the actual system, and I'm going to take the identity here, and I'm going to take +1 here. So what does that +1 mean, really? We're taking the natural numbers times this, set with a single element. We're going to the natural numbers, and we're going to take n, comma, dummy element, and we're going to go to n+1. So this is a clock. That's the idea. This is a very simple kind of clock system in this setting. And I could do this. I think we've covered this before, and we also covered the ones that stop by allowing you to potentially stop. Maybe I should run this example in that case because it would be useful. But for now, I'm just going to do this one. Now, WC, I'm going to take WC to be id of this interface. Just going to do what I said before. Um, it it's worth noting that I don't think I have a choice here. So I'm going to run this through live, but I think that this is the only choice you can make in this double category. The reason is if I had another thing like this, right? Then, oh no, right. And then I have to have a comparison of this to the identity. So I have to have a square, which is a globular square, with the identity here. Because this is a comonad with respect to lens composition. As in, I'm looking at this part of the structure here.
Why do we know it needs to be globular?
Because both of these are globular.
Okay.
They're part of what it means to be a collax double functor. This part of the structure is a collax double functor. And so the collaxity of the collax double functor is always globular. And so what you see here is that the bottom square says that WC equals id, and the top square says that WC sharp equals id. So I don't actually have a choice, just to point that out, which is good because I never noticed you could potentially have a choice until quite late in this. But it turns out in the cases I was most often considering, you really don't. You always have to consider this to be the identity. And you could still, like, once it's the identity, you could still end up with this, but I'm pretty sure that like something like this now kills you. Oh, excuse me. Something like this now forces this one to be the identity as well. Simply because we note that this one is actually the identity of that, and this is actually equality. This is be a strict double category, so this must also be the identity. In any case, it has to be an isomorphism. So you're really getting no more data doing this. So the point is that we are in, and moreover, this is Cartesian in the vertical structure. So this other stuff here kicks in, and this is all determined by diagonal. So in other words, we have C to C tensor C, right? What does that look like? Well, that's N, and this one's N tensor, and on this side too, right? Star N, star N, tensor, star, right? This is what this thing would be, and this is the one on IC. These are both charts, right? But this is of the form FF or whatever. This is a map of systems, right? We don't know what it is yet. And it has to make this commute, right? But I actually know that this is equal to n times n, but this is by definition or by construction, you could say. And this is star times star over n times n, right? So I can actually take these to be the diagonal in both cases, and that will make everything commute. In fact, I'm forced to by the fact that this has to be a commutative comonoid structure, and these are Cartesian categories. So again, in this case, in the case of these discrete time Moore machines, and as you can see, this argument was fairly general, and I would say that it applies this way to any of these Moore machines whose underlying thing is these simple lenses of this form, right? But as you can see, you're actually the all the structure is highly constraining. So in this case, all we had to do was pick the clock, right? Everything else was determined by the various constraints it was under, right? WC had to be the identity, which was this weird sort of thing that I didn't really explain. It just was up there because it's what part of a collax morphism is, but we end up computing it has to be the identity. We end up finding that these diagonals here have to be, these things have to be the diagonal, and this thing has to be the terminal map, because one in this case is in fact terminal. And you'll have to believe me, but this also has to be the identity. So you end up with, or at least an isomorphism that's like very close to the identity. So you end up with essentially just this choice of clock. Okay, so what do we do with this is what yeah, sorry, go ahead.
It's and the reason that the map C to C, so on the left-hand side, you'll always get unique choices when your Cartesian, when your Monodal structure is
Yeah.
Cartesian.
Yep.
Is that what we're seeing here?
Yes, yes, exactly. So one thing to remember is that you can just like select out little bits of this and do your argument on each thing. So if this is a cart, when I say the monodal structure is Cartesian, I do in fact mean that each of these categories is Cartesian and each of these functors preserves Cartesian. That turns out to be equivalent by symmetry of internalization, one of my favorite theorems. Um, so here is a collax morphism, symmetric monodal category morphism, right, into a Cartesian category. And we note that that must be determined by the structure on it must be determined by the diagonal because there's a I could run through the argument, but there's a unique co-commutative comonoid structure on everything in a Cartesian category that is given by the diagonal, and you compute that using the universal property of the product and the equations governing this.
And the thing on the right is always going to be like we've got this property that these the double category of interfaces is like flat.
Yeah, it's flat here. There's in most one cell in here, right? There's no data in there, which is an important component of this, right? Yeah.
So it's always got this property where it's got three identities and the top one can only the identity, which is
Yeah, at least it's isomorphic to the. Well, it's not generally true that just because you're thin.
not really.
Yeah. It's not super it's something is specially going on by the fact that once we get it in this form, we actually look at the definition from over here and we then check that in fact this implies that everything's the identity. So it's slightly stronger. I'm sure there's an abstract thing going on here.
Is this something's a vibration, a discrete vibration? Is that what's the source and target maps or something?
Maybe.
Like C1 to C0 times C0 being anyway, that's not.
Something you're saying like these?
Yeah, like if you can have each one independently be a vibration, but if you've got the pair being a discrete vibration, then that's sort of what you're saying, that downstairs a map, a pair of C0 maps, and there's a unique.
Right. I don't think that's happening here either, in general, at least. It's just the case that like such a square is given by two squares. And the bottom square is just identity, identity, identity equals identity. Or like identity, identity equals this followed by identity, which just means that that bottom one equals the identity.
Right.
And then the top one is like you have to do reshuffling and stuff, but everything in here is so trivial, it just forces it to be this as well. So it's not like surely there's some more general thing you can say, but for now, let's just say that like for more machines, pretty generally, it's going to work out to not be an extra choice. And I will also note that you will always be able to choose it to be the identity. It's just in this case, we are also forced to make that choice. So which is a thing I will emphasize is that the clocks you put in your systems theory are a choice. They're not naturally determined. So like you could always choose this part of the thing or like this whole part of the thing to be a bunch of identities, which is what I will usually consider. You just have this freedom. The argument supports this freedom. What is the argument, right? Okay. If you remember the beginning of this about 15 to 20 minutes ago or whenever, right? So we have C, which is like going to be our clock, and it goes into our system theory like this, right? Again, I'm like C, I C, blah, blah, blah. And it's a collax morphism, as we saw that if our system theory is nice enough, that's sort of everything. But then remember what we did is we turned this into I'm just going to start writing this as S because I'm getting a little like, I'm going to use S meronymically for the whole module. That's okay. Right? We turn this into a discrete op vibration, a strict discrete op vibration. And then we're going to turn this into a lax functor into omega, which again was the module. Span set 1 dash acted upon by span set. Okay. So, and I will call this SC dash because we'll compute it right now, right? What does this do, right? It takes an S in here, right? And it sends it to the set of all pairs of all things that project of the inverse image of this projection. What is the inverse image of that projection? Well, it's the set of all maps from C to S, right? Well, it sends it, it's sending it to a system. So remember that such a map is actually like we have, you know, S is some system in interface I. And so we put down here, S is some system in interface I. And up here we put C, and here we have IC, and then we have a square, the set of all squares like that. And down here, we just have IC to I. Okay, so what does that mean in our particular case? E.g., like we have, plus one id and n, n star, which goes from star to, let's call it more machines, discrete time, more machines, simple more machines, we were talking about up there. Right? So, okay, we take that and we get this other thing, which is, let's call this clock, right? We get clock, down arrow more, over more, and we turn this into more, going into omega, which is more out of the clock. So this sends a more machine to this system in here, which again is it's something over the interface, over something in the interface of some things, right? So it sends it to the set of all maps from the clock, right? In other words, all charts of this form. Well, where the constraint on the left-hand side, I've described this before. Oh boy. Ugh. Where are we? Okay. Go. So it's the set of all things like this, such that this commutes, or is, in other words, the set of all squares of this form, right? And here it's star n dash dash I O. So and this is the projection that just projects out that right-hand side. Okay, so what is this? Again, let me rewrite that. This is all I. This is O from N to O, and I from N times star to I, which is essentially the same thing as just N to I, right? So again, these are, in other words, this is a sequence of outputs and a sequence of inputs. Over here, we have that I and that O, and we have an S from N to S, such that, right, the equations hold that make that square commute up there, which again is that E of ST is equal to OT, and U of STIT is equal to S of T plus 1. Right? So as you can see, we have successfully taken a Moore machine and sent it to a Jan Willem style behavioral system, right? Which is to say, a system with some time varying variables exposing some of those variables, right, as parameters. And what are the parameters we're exposing? Well, it's a stream of inputs and a stream of outputs. So they're not I say variable, I say parameters. I mean parameters and variables, right? They're sort of indistinguished in this. They're how you want to use it, right? So here we have I, we have O, and over it we also have a stream of states that satisfies this relation. So as you can see, the image of this in here is the streams of inputs and outputs which are achievable by this system, right? Which is to say the graph of the transformation that this system is computing, if you will, between inputs and outputs, if you want to think of it that way. But this is a perfectly sensible way to understand the behaviors of this system, and where we've exposed the observable behavior, and we also have, as part of the variable here, the actual parameter to our system. What's the functoriality here, right? Okay, well, we take that thing. Let me take this and copy it. We'll move it back over here. Right? So we send it to a span. Right? So here is going to be the same sort of thing. So if I have now a composition law, WW sharp, which again, as we saw earlier, can be presented by a wiring diagram, right? Then we take that composition law and we put it here. And here, we would actually put WC. But in that case, it's the identity. Right? Right? Now, this is a composition law in the variable sharing systems theory here, right? So if we compute out what this is, right, this is the I's and O's over here. This is I prime, O prime. This, as you can see, is actually triples. Quadruples, I, O, I prime, O prime, but they're satisfying some relationship. And that relationship is W of I of t. Remember, these are streams, right, of sequences. W of I of t, sorry, W O of t is equal to O prime of t, and W sharp of O of t, I prime of t, is equal to I of t. And the reason it's the same t all the time is because we have this identity in the back here, right? So again, this is just what it means for this to be a square in the double category of lenses. Okay? But now remember, if we had a wiring diagram, right? Something, for example, here's an example, a wiring diagram, right? What you can see is that this is the relationship, this set is the set of all streams of things at all of these. So the outer inputs, the outer outputs, that's this stuff. The inner inputs and the inner outputs, that's all of these. And they have to satisfy the relationship that if your inner output is wired to your outer output, they better be the same value here. They're going to be set equal. They are going to be shared. Why? Because they are connected by this wire. They are the same value in the variable sharing world, right? Similarly, you're going to do that here. You handle all the other ones, right? You say, oh, if I take an output here and my inputs here, I'm going to make sure that they're wired together with all the inputs in the inner inputs. So I take my outer inputs and my inner outputs, and then I set them appropriately to the inner inputs. Right, cool. So what is composition in the variable sharing systems theory? It's pullback of these. In other words, this pullback here, right? This is going to be the set of behaviors of the inner system, right? Together with behaviors of the outer interface, right? So this pullback here is going to be things in here and things in here that agree down here, right? So in other words, it's a behavior of the inner systems together with the behaviors of both the inner and outer interfaces, right? Such that the inner interface one is the same as the one from the system. So we're feeding that in. So in other words, it's just the whole behavior here and this stuff such that they agree via these relations, right? That's what lives up here. Now, there's another thing we can do, right? Which is we can consider the behavior of the composite, which I'll put up here, right? It's NN to SS. But now we compose inside. And this lives over here, right? So this one also lives over here. And now the claim is that we have that the fact that this is lax means that there is a map like this. Oh, there is a map like this. There we go. So what does that mean, right? What that says is that if you have a behavior of the inner system, right? And if you have a stream of inputs and outputs for the outer interface that agree with the inputs and outputs of your stream of your behavior you have here, according to the law determined by the coupling law, which are these two equations, right? That's everything that I've just described what's in this set. You can produce a behavior of the composite system. How do you do that? Well, it's by composition. To be very clear, the behavior, what I'm saying is that, again, I'll sort of write it out. I have NN. This is my clock. This is my N star. I have W of the clock, which is actually an inequality here. So I'll write that here. I have a behavior here. I have a behavior like here. I have my wiring diagram here. So this is UE, this is W sharp, O prime, wiring diagram, coupling law, etc. I have my outer one here. Both of these commute. So then I can take this, and then here's where the colaxity comes in, by the way. I'm gonna draw it out quite explicitly, right? So N. This is equal. Here's my clock again. And this thing here is actually this thing here, right? Well, it's the identity in this case, just because this happened to be an identity. But and because we're, as we mentioned, we're in this sort of special thing. But what it is this in the abstract. Because this is sort of, that's clock, this is WC. It's the identity here, but it's WC. And this is the colaxeter, which you might call clock WC bar, something like that, right? Which, again, in this case, is just the identity. And so that's that, which is cool. And you get that for every single kind of composition you have, because this is a lax in all ways. So what I've shown you is that by abstract nonsense, right, we can take any of these colax points. In other words, which are systems with very minimal kind of structure. As you've seen, the structure you have is quite minimal. In many cases, as we've seen in more machines, that structure is trivial and you're just taking a single system. That's your input data here. But in general, this has to be colax. I'm going to make that there. This is colax. We then form the comma. The comma is sort of just a pit stop in the middle. And the nice thing about it is it's a strict discrete op vibration, right? For our thing. We then also have classifiers for strict discrete op vibrations, which we've already covered. So we get a lax functor which is defined by sending everything in here to its inverse image in here, which is defined as the maps from C out. So this is a representable functor. In the ordinary sense of category theory, representable. It maps out. But as you see, it lands in set, sure, but it lands, in fact, in this Jan-Willem style behavioral control theory, variable sharing systems theory of omega, which we computed from the abstract nonsense last time. Yeah, so this gives us a number of compositionality results. And we can in fact do a little better than what this gives us because it's like completely lax. It's completely lax, but it is in fact possible to note that in certain cases it's more pseudo than that. So in full generality, it's totally lax. And that's because there is the capacity for coupling to induce emergent behavior, right? However, in more situations than you might think, you can actually get it to be pseudo on a lot of things. In fact, for this example, it will in fact be pseudo. Which doesn't seem like a thing that should happen, but the way it happens is because you are in fact keeping track of these outputs as well. And so it's helpful. So there is in fact a theorem. I guess in the special case it appears, yeah, in the special case it appears in my manuscript. In the general case, Matteo Capucci has expanded it quite far more generally to systems theories in general, but I think I forget that particular form. But in fact, if you're in a Moore machine setup, a lens-based setup, and the output of your clock is the identity, then this entire thing will be pseudo.
Sorry, if you're in a Moore machine setup and the output of the clock is the oh right, so the WC bit.
No, not the WC bit. In fact, the output part of your clock, this bottom part of it. It's something that's very special to Moore machines.
Oh.
Although Matteo formulated it abstractly. I'm just forgetting the precise formulation of that. So let me go into that for a little bit. So first of all, I'll have you note that it's lax, in particular, it's lax monoidal. What does that mean? Well, that is again similar, right? Similar to this sort of thing. If we have, behaviors, I don't know how many times I can draw these squares in full glory, but I'm going to do a lot of copying here. Oh.
So just
Yep.
to ask about that pseudo versus lax functoriality. Is that so? Just interpreting it in terms of this bottom left diagram, is that saying that if we've got a decomposition of the bottom row as a system and a composition law, then there's a square, a cell filling this picture is equivalent to two cells at the bottom.
Yes, that's right. That's right. It is indeed the case that every diagram of this form factors uniquely as this.
Right.
And that has to do with the fact that the lens double category is what I've called Spanish. Right. And the select definition of Spanish is that all the Poiret representables are pseudo. That's exactly the conclusion we're aiming towards. What it does mean is, in fact, for every map out of it's okay. Sorry, it's a little. There's I'm not covering. There's also you also need the property for two wiring diagrams for there's a lot of lot of laxity involved in these. So you also need the property for there, which comes down to the Spanishness of the interface category. So this is actually not, I may want to go through that at a slower pace because it's actually very useful. And it is also, it's a good reason to cut down from general hypergraph categories to so we've covered the cospan composition of cospan finite set composition. If you restrict the left leg to be epi and the right leg to be mono, you'll end up with a Spanish double category.
Okay.
even though it's filled with cospans.
Yeah.
And this has to do with the fact that finite sets are adhesive as a category. And
Mm.
so as a fun for that reason, you can actually, if you restrict your coupling laws of that form, which is extremely, like in my opinion, the sort of also just intuitively the correct way to restrict the variable
Mm.
sharing ones, where you share and then maybe you re-expose some of the things you've shared.
Mm.
You'll end up with at least a pseudoness on the interface part. Um,
At least students on the interface part. Right,
yeah,
okay.
because this is also lax double functor on interfaces. So I
Yeah.
guess I didn't cover that, but it's lax in every possible direction.
Oh, right, the compositionality for right, okay, okay.
Yeah, it's lax in every possible direction, including with tensor. Let me cover the tensor for a second here. So here's my right. So here is this, and then I want to paste one more, but this one I'm going to do the tensor. Yeah. So a lax monoidal thing. Here's my tensor here. Uh, so the lax monoidal structure, this product here is the monoidal structure of set, or omega, really. And this tensor product is the monoidal structure of more, right? So this is the monoidal structure of omega, and these are the monoidal structure of more, right? So laxity means I go from the monoidal structure of the codomain to the image of the monoidal structure of the domain under this functor, right?
Mhm.
And so I've written that shape out like this, right? So just to be really nice and explicit, this is more clock S. I'm just going to write it as S, right? Times more clock S prime. And this is here is more clock S tensor S prime. But remember, Moore machines were a Cartesian systems theory. This tensor product down below, while it is a tensor product with respect to the lenses, it is a Cartesian product in the direction of these type maps. And it being a Cartesian product means that this is an isomorphism. That's what it means to be a Cartesian product. It means that maps into it from anything split as pairs of maps. So that's your pseudoness in this case for that. The pseudoness on this on the left hand side of the screen for this is more involved, and it involves actually looking at when you actually look at this, and you actually look at the fact that the clock exposes an identity here, and you see that in fact you only need that if you have a behavior, you can always define this middle one from the data you have of this and of this, because this thing's an identity. So you can define this one to be this after this, and then the other one you can define this part, the I part, to be this and this. And that's intuitively what it is, and it just works. So you get pseudoness of tensor, you get pseudoness of this, which is for dot. You get pseudoness like system acted upon by interaction. You also get pseudoness for composition of interactions. So in general, this is lax, but I will say that often pseudo. And pseudo functors of this form are what you would really want to call compositionality theorems. So I think I may stop here and try to do one of these all the way through a little bit cleaner next time. But this is the pipeline for producing compositionality theorems in the abstract. And in fact, what we'll see is that we can now take a category of such clocks and turn it into a category of such functors, and then and understand that as instead of landing into spans of sets, you'll land in spans of functors from that category into set.
Right. So that here we're taking commas, but only where the thing on the left is.
No, so I should. I guess I want to go into that later, but it's not where you think. We're not going to replace star.
Right. Okay.
We're going to work at the level of mapping from a category into the set of the category of collax morphisms and do it like that. And at the very end, we'll notice that the power of omega by a category is in fact spans in set to the category. Okay.
Okay.
Sweet.